The Air Force Small Business Innovation Research Program has funded the development of technologies vital to the production of the F-35 Lightning II. This is the story of one of them. America's newest Joint Strike Fighter, the state-of-the-art F-35 Lightning II, is one of the most technologically advanced airplanes ever built. A large part of the airframe is made of titanium, half the weight of steel. While it's a superior material for aircraft construction, it's not easy to work with.
In order to build the Joint Strike Fighter, there was going to be more machining that needed to be done of titanium on those airplanes than had essentially been done in the history of the world before. Titanium is difficult to machine because it's very, very hard, and it also has a very low thermal conductivity.
This means that tools used to cut titanium quickly overheat, which greatly reduces their life and is very costly. To overcome this disadvantage, the cutting tool and the titanium need to be significantly cooled down. Traditional cooling methods involve flooding the cutting operation with liquid coolants, which can be an environmental hazard. In 2002, Creare, a small business located in Hanover, New Hampshire, that specializes in research and development, began investigating methods for improving the titanium machining cooling process.
We had a small business innovation research grant from the EPA. The main objective of that particular program initially was to remove coolants from cutting operations, which tend to have a lot of biohazards associated with them.
The answer: cooling the cutting operation with liquid nitrogen, the byproduct of which is a harmless gas.
Very early on in this program, we found that having a high liquid fraction of liquid nitrogen at the cutting edge was really effective for removing heat. The real trick is figuring out how to get it there from a fixed source or from wherever you're getting it from through your machine tool. And so we had to come up with a unique technology, what we call our through-spindle lance, to route liquid nitrogen from the top of the spindle to the top of the tool holder, basically, and do it in a dynamic way. Developing that through-spindle lance was key for integrating the technology. It turned out that our initial system that was built during that time period significantly outperformed standard flood cooling. And so because of that, we began to think about other applications of the technology, because now you not only have a prevention benefit, but you have a processing speed benefit.
Following the initial EPA award, Creare received crucial SBIR contracts from the Air Force, as well as other government agencies, that led to the eventual success of the cryogenic machining process,
where we actually did one-to-one comparisons at a Tier 1 supplier for F-35 of flood cooling and liquid nitrogen, and we were able to clearly show that using cryogenics was a big win, both in terms of cost and quality for titanium machining. 5ME purchased the patents from Creare, so they own the technology. They actually can put it on any machine, anywhere. They're working with some of the major players in the machining industry to try and bring a more broad base of available tooling, for example, to bear, so people like Lockheed Martin can implement it broadly throughout their manufacturing base.
Lockheed Martin is using the technology to really drive affordability in their F-35 Joint Strike Fighter program by reducing component cost up to 30%. That is a total of $300 million for the program.
We've developed a very sophisticated delivery system. It is machine tool friendly. It'll run through conventional and new machine tools without allowing the cold to dissipate into any other member of the machine tool. The second, and possibly even more important from a performance perspective, is the tooling technology that was developed to handle internal cryogenic flow.
With the retrofit kits that 5ME supplies, it offers the end user the flexibility to use through the tool liquid nitrogen coolant or external flood coolant. That's important depending on the type of material that the customer may want to process. The vision for cryogenic machining technology is to replace the conventional coolants that are used today in industry, as well as machine the new, stronger, lighter materials as efficiently as the materials they replace. I think what the technology will do is it'll allow the material producers to produce materials that have not been previously developed because of the limitation in machining.
The SBIR process was instrumental in making the cryogenic machining a success.
Without the SBIR program, I doubt that the technology would have happened. Simply because SBIR allows you to do sometimes out-of-the-box, innovative things that others may be very skeptical of or be very reluctant to invest in.
Along with manufacturing aircraft parts, this tool cooling approach can be used for other high-performance machining applications involving titanium, stainless steels, alloy steels, and ceramic matrix composites, and is a perfect example of how the Small Business Innovation Research Program helps the Defense Department meet its better buying power goals of controlling costs while getting effective new technologies into the hands of U.S. warfighters. Learn more at www.afsbirsttr.com.